this question, we will be learning the relationship between electric field and electric potential, as well as electric potential due to different charge distributions. There are two parts to this question. Let's take a look at the first part of the question. The diagram below shows a uniform electric field in which equipotential lines are spaced 5 cm apart. A charge of negative 2.0 microcoulomb is placed at equipotential line X. Calculate the magnitude and direction of the electric field. Before we proceed to solve this question, there is a need to understand certain important terms in the question. What is meant by a uniform electric field? An electric field is a region where an electrostatic force is felt by a charged body placed in the region. Now, this electrostatic force is not a contact force. It is a force felt at a distance. So usually this electrostatic force is an attraction between unlike charges or repulsion between like charges. An electric field is a vector quantity, meaning it has magnitude and direction. So when we are talking about a uniform electric field, we mean that the electric field has constant magnitude and a direction that is always in the same direction. The question asks for the magnitude and direction of the electric field, so it's actually asking for the electric field strength. Electric field strength is an alternative term for electric field. So what is electric field strength? The electric field strength at the point in an electric field is defined as the force acting per unit positive charge placed at that point. It means that if you place a positive 1 coulomb in this electric field, this positive 1 coulomb will experience an electrostatic force. And this electrostatic force experienced by a unit positive charge of 1 coulomb will be known as the electric field strength. Now, another term that needs further explanation is the equipotential lines. What are equipotential lines? Equipotential lines are lines on which the electric potential is the same at all points. Meaning, if you see in the diagram the dotted lines, any point on the dotted line will have the electric potential as stated in the question. But what is meant by electric potential, you may ask? Well, the electric potential at the point in an electric field is defined as the work done by an external agent to bring a unit positive charge from infinity to that point. Well, it just means that if you want to bring a unit charge of 1 coulomb from outer space to a point in the electric field, there's a certain amount of work that has to be done. And this work done is known as the electric potential. There are certain characteristics that you need to know about equipotential lines. Equipotential lines are always perpendicular to the electric field. So you can see that the direction of motion of the charge is perpendicular to the equipotential lines. So very likely, the direction of the electric field could be along the direction of motion of the charge. So, with an understanding of all these terms, let's proceed to solve the question. Now, what is the formula needed to solve for the magnitude of the electric field strength? The formula is given by this. E, which is the electric field strength, equal to the potential difference, written as change in V, over the separation where this potential difference occurs. Now let's refer to the diagram given. Let us focus on the 50 volts and the 30 volts. Alright, so between these two, there is a potential difference, change in V. The separation is 5 cm. So 5 cm. So let's substitute all these values in. Now the change in potential or the potential difference is 50 minus 30 volts. That is the potential difference. Now the separation where this potential difference occurs is 5 cN. But I have to write that in meters. So it will be 5 times 10 to the minus 2 meter. So upon calculating, my answer will be 400 volts per meter. So the units for electric field strength can be written as volt per meter. So the magnitude of the electric field strength is 400 volt per meter. But electric field strength can also be written as 400 Newton per coulomb. Because recall, electric field strength is also defined as the electrostatic force acting per unit positive charge. Now force is in newtons and charge is measured in coulombs. So force per unit charge can be written in units as Newton per coulomb. So we have settled the magnitude of the electric field strength. Now how do we calculate or find the direction of the electric field? Now it is very important that you note that the direction of the E field is from X to Z. Electric field flows in the direction of decreasing potential. And from the diagram given, the potential decreases from X to Z. So along that direction, that must be the direction of the electric field. And since we know that electric field lines are perpendicular to equipotential lines, the direction of motion of the charge will indicate the direction of the electric field. Let's take a look at the second part of this question. Two charges P and Q are 100 mm apart as shown below. X is a point on the line between P and Q. If the potential at X is 0 volts, what is the distance from P to X? Now, before we can start solving this question, it is very important that we know certain terms and the formula that's needed to solve this question. Now, we are required to find this distance where the potential at point X is 0. So we need to have a clearer understanding what is meant by potential. So let's say we have a charge Q and a point X, and this point X is at a distance R from charge Q. Then, if we were to move a positive 1 coulomb from infinity to this point X, then the work done is called the electric potential, and it is calculated by this formula, where V is the electric potential, which is the work done to move a unit positive charge from infinity to this point X, where X is a distance R from charge Q. The formula is V equal to Q over 4 pi epsilon naught R, where epsilon naught is a physical constant commonly called the vacuum permittivity or permittivity of free space, while the value is as shown is around 8.85 times 10 to the minus 12 farads per meter. Let us proceed to solve the question now. Now the question says that the potential at X is 0 volts. X is a point on the line between P and Q. The question never states where is X, so let's arbitrarily say that X is here. So this is point X. So I'm going to call the distance between P to X D, and the distance between X and Q to be 100 minus D. Now previously we stated that the electric potential is given by this formula, V equal to Q over 4 pi epsilon naught R. And we're going to use this formula to calculate that distance d. Now, here there are two charges, P and Q present. So at point X, the combined or the resultant potential must take into consideration the charges P and Q. So we have to do some addition later. All right, let's start off with the potential at X equal to 0. This is what is given in the question. Now, at point X, if you want to calculate its potential, you must take into consideration charges P and Q. Let's find the potential at point X due to P. Then we call this VPX. That is the potential at point X due to charge P. Then we add the potential at point X due to charge Q. Both potentials can be added together because potential is a scalar quantity. So the direction is not required. So the two added together will be equal to 0. Because we are looking at the potential at point X due to two charges. So we just simply consider individual potential due to each charge at point X, VPX and VQX respectively, then we add them together. Next, we will do some algebraic manipulation. So VPX is actually negative VQX. Now let's use the formula now. The potential at point X due to charge P is the charge at point P over 4 pi epsilon naught times d, because X is a distance d from charge P and is equal to the negative of charge Q over 4 pi epsilon naught 100 minus d, because point X is 100 minus d mm away from charge Q. Then we proceed to put in the so-called variables that's given to us. So charge P is 4 microcoulomb. So 4 micron over 4 pi. Then epsilon is 8.85 times 10 to the minus 12. And D. D is the unknown. And Q is negative 6 microcoulomb. So negative with a negative 6 micron coulomb, and over 4 pi epsilon naught, where epsilon is 8.85 times 10 to the minus 12. Then 100 minus d here. So this is the two equation. So let's solve this equation. So the micron can cancel on both sides. The 4 pi also can cancel on both sides. The epsilon will also cancel on both sides. So what we are left with is just 4 over d is equal to 6 over 100 minus d. And upon solving, d is equal to 40 mm. Why is it 40 mm? Because we leave our length in millimeters. So I hope with these two examples, you'll be able to have a better understanding of electric field and electric potential. Thank you.